Okay, let's go ahead and get started. So the semester ends 3 weeks from today. I was always surprised when I look at the calendar and say, whoa, what happened to the semester? So let me just talk a little bit about scheduling stuff. We have a Lab 6 that's due today. Lab 7, which is originally due next week, is actually, we extended the deadline to be due basically 2 weeks from yesterday. The idea is to give you that weekend to finish it up. Lab 7 is a little different than our other labs. There's actually nothing to submit in the sense that there's no automated test. And so, the notion of due for Lab 7 is more of a virtual due. The actual rubber meets the road at your checkoff, which is due at the final deadline of the course, as is everything, which is Thursday, the last day of classes, Thursday, May 12th at 5 p.m. And so after that, the website simply is not going to accept any other things. So just plan to, and you can't use your late days to extend that because we can't go past the end of classes. That's the way the Institute runs its rules. And in fact, we'll be giving out grades on Friday the 13th, oddly. The day after the last day of classes. So there isn't really much opportunity after the last day of classes anyway. So, any questions about the final scheduling? Oh, quiz 4, which is the Friday, May 6th. Some people, if you add up your points and you decide that you don't need to take quiz 4, you're welcome not to take it. And so there's always a few lucky folks who've managed to score big. Typically, there's the sort of folks who can't not take the quiz. So, so they often show up anyway. We've had in the last couple of years one person that scored absolutely every point that's possible in 6004, all 215 of them. You can go for that too if you're in the running. A remarkable performance. He's the sort of person that when we would grade the exams, we would grade his first just to see if we got any of the answers wrong. That's so. Okay, so we've been talking about operating systems. And what we're going to do is continue that conversation today. And let me just sort of go over what, for 2 minutes what we've talked about, and then we'll basically extend the conversation through this lecture. So the blue area here, this big hunk of blue, is basically a bunch of special code that we write, that we call the operating system, whose job it is really to deal with all the low-level hardware of the machine and create the impression of virtual machines to be used, separate virtual machines, to be used by each of the processes, the user mode processes that's running. There's only 2 ways to start executing kernel code. One is through an interrupt from an external device. In this case, I'm showing you a timer that goes off every 60th of a second or something like that. The other way, which we'll see again in a second, is through only legal opcode. So that's the only way in which kernel code starts running. And so the way time-sharing system works is what happens is that every 60th of a second, an interrupt gets generated by the little piece of hardware, and that will interrupt whatever user process is running. Let's assume it's process 1 for the sake of this discussion. And so we enter the kernel here, and we start running the code at the timer interrupt handler. And the first thing that code does is to take all the user registers and copy them into this little, we called it the M-state data structure. The machine state, it basically is just a temporary copy of all the stuff the user has put into the registers, including the PC, because remember, when we took the interrupt, we put the PC plus 4 value of the interrupted instruction into the XP register, and of course that's one of the registers that's saved. And the reason we save all the registers, one is it makes it very easy for the kernel to access the user's register should it need to do so, and secondly, it allows the kernel to use the registers of the machine for its own purposes. So having done that, there might be a little bookkeeping incrementing the time of day, and then every so many clock ticks, the timer handler, as we saw last time, calls the scheduler. So the scheduler is a little piece of code whose job it is to implement the time sharing of the system, the ability to give each of the virtual machines, each of the processes, a chance to run. And so the way that works is pretty simple, actually. It copies all the saved registers for the currently running process into the process control block, which, among other things, keeps a copy of the user's registers, sort of an archival storage. It saves them away so that it can restore them next time it's time for that process to run. The scheduler then goes to the next structure in the process control block here, the next process control block in this big array of PCBs, and it takes the registers that it finds there, in this case the registers for the saved registers for process 2. So process 2 at some point in the past stopped running, it got interrupted, and the scheduler saved his registers away, and what we're going to do is take those saved registers, different contents of course because it's a different process, and copy them back into this temporary buffer. And the reason we're doing that is the timer interrupt will basically, as we start now exiting from the, returning to the running user mode from the timer interrupt, it basically takes all these registers, puts them back into the actual hardware registers in the beta, and then returns to wherever it returns to. And in this case, what it will do is it will basically resume execution of a user mode program because we've done this swap of the user registers and reset up the memory map context and things like that. What we've done is arranged to interrupt process 1 and resume execution in process 2. So the net effect of this is to transfer control of the machine from process 1 to process 2, and it's the kernel's job to actually do all the low-level moving around that's necessary to create that. So that's how time sharing works, and that just happens again and again and again, and we eventually deal with all the user mode processes in a round-robin fashion. Okay, the second way to get into the kernel is you execute the so-called supervisor call instruction, which is in fact not really a hardware instruction in the sense that your Lab 5 beta knows what to do with it. It's just an illegal opcode. So it's just like any other illegal instruction. We happen to take one of the illegal opcodes, in our case opcode 1, and devote it to communication with the kernel. So the way you, quote, call the kernel is to basically execute a particular brand of illegal operation. In the low order bits of that instruction or a little index saying which supervisor call you want. It may be that what the user does, if there's some arguments that need to be passed to the call, you're telling the kernel you want it to type out a character for you. And so so the way we're going to do that, a simple little hack, is to simply put values into the user program puts values into its registers, which of course gets saved away when we come in here with the illegal interrupt handler. Like every interrupt handler, it saves away the user's registers. And in fact, the particular supervisor call may access the user registers to either get values the user is sending into the kernel or to put values into the user register data structure to be returned to the user when execution resumes. Okay, so once that, whatever the supervisor call does, it does, and when it's time to return to the user, it reloads the user registers, perhaps modified by the supervisor call. So this gives the ability for the supervisor call to return information to the user program, and then we resume execution, presumably with the instruction following the supervisor call. Okay, so those are the two things that we have discussed. Basically the whole scheduling time sharing system and the fairly simple strategy for asking the kernel to perform services for the virtual machine in which you're running. And today what we're going to do now is to add one last set of things to talk about, which is basically how do we deal with I/O devices. And you'll see we sort of have a two-pronged strategy. One is the I/O device uses our regular interrupt system to communicate with particular pieces of code in the kernel whose job it is to maintain basically buffers of keystrokes or mouse clicks that are coming in from the user. In the case of an output device, it might maintain buffers of network packets to be sent out on the network, whatever they are. So all the I/O devices basically ask the kernel to do things via interrupts. And how does the user communicate with I/O devices? Well, with supervisor calls. And what we're going to spend the next 20 minutes or so doing is to actually look at that mechanism and see how it works. Okay, so we're going to talk a little bit about how both a keyboard, characters from the keyboard come in and get filled into a kernel buffer, and then we're going to discuss the implementation of a particular supervisor call read key, whose job it is to get the next keystroke and return it to a particular program. So I have a program, it wants to read a key from the user, it will make a call to the kernel, a supervisor call, and hopefully when it's time to, when execution resumes, the next keystroke from the user will be in the user's R0. Okay, so come along, you hit a key on your keyboard. The keyboard basically signals to the kernel, I have a character, please come get it and do something with it. The kernel will basically read that character from the keyboard. We'll see a little bit more of that code in just a second, and basically arrange to stick it into, in this case, a little circular buffer in the kernel. And slowly fill up that circular buffer. What happens, by the way, when you try to type too many characters and the kernel buffer fills up? You've experienced this probably. Well, so one thing you could do, which would be a very bad thing, is to simply ignore, fine, I've accepted your 20 characters, the 21st is just going to disappear into the vapor. So that sort of doing bad things silently is never good practice. So another thing it does is it beeps. Ever done that? You type along, all of a sudden going beep, 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 and you're going, what? Who? Huh, what did I do? And the answer is the hardware, the low-level kernel system has carefully been copying all your characters, but it's run out of places to put them, and it's just telling you that I didn't listen to that last character. So it's trying to give you some sort of feedback that it isn't happening. So, some other process has to wake up, and user mode process has to consume characters before you're allowed to fill up any more kernel space with characters. Now the user mode program is running, it wants to read a key, it will go off and execute a supervisor call, we'll end up executing a little piece of C code that says, oh, there is a character, good, what I'm going to do is I'm going to take it out of the buffer, and it returns it to the user in the user's R0. So when we return from the supervisor call and resume execution of the instruction following that illegal opcode, the user can expect to find in R0 the next key. So, so as a user program is consuming characters, the keyboard is producing them, and we have kernel code that somehow gets those two things hooked up. Okay, so first of all, notice that the incoming the interrupts from the keyboard are absolutely invisible to the user. So when a user mode program is interrupted and the kernel handler does something and resumes execution of the user mode program, mostly the user can't tell. If it is keeping close track of the actual time of day, it might notice that there's occasional times when between one instruction and the next, a couple of milliseconds has gone away. But other than that, you can't tell. Though, nothing about the machine state that's visible to the user program changes. Okay, so it's completely transparent. Here we can see down here what it might look like. The hardware may, in fact, represent the devices basically as memory locations. So many architectures, what you have is either a special portion of the kernel address space, or perhaps even special instructions that are like load and store, except they access a special address space, the so-called I/O address space. And you can basically reach out, and there's probably a byte register that gives you the key number that was pressed, maybe some sort of flag indicating that there's a character available from the device. So if I hit a key, I would expect to go see the flag be 1 and whatever the key number is. Often the kernel performs services like translating key numbers into actual ASCII characters. So, you plug in a new keyboard and the operating system chit-chats with you. What format is your keyboard in? Do you have the Swedish keyboard? Or, and so after you've negotiated with the OS about what format of the operating system is capable of taking key numbers and turning them into characters. Most user programs, you can ask for key numbers, but most user mode programs just really want, if I type an A, I want to read an A. I don't want to read key 103 and figure out for myself what key that is. Okay, and then this is a very simple procedure where there's a set, basically the keyboard, a particular process has the keyboard focus. In other words, if I type on the keyboard, I expect characters from the keyboard to go to that process. So each process would have its own little circular buffer of incoming characters. And you might negotiate separately with the Windows system to change the focus of where you're typing. All of that sort of Windows system code and things like that is way beyond the scope of what we're covering. So we've come up with some way, though, to identify the buffer for a particular, that the keyboard data should be put into for a particular process that has the keyboard focus. So this is just a little bit of code to stick the character in the buffer. Okay. What does the read supervisor call look like? Let's figure that out. So here's the read supervisor call. What we're going to do is we're going to execute a couple of instructions. So this is the handler, right? So there's a little assembly language stub that looks to see which supervisor call the user has made. If it's the read key 1, which is number 6 or something like that, it says OK, and it dispatches to this particular hunk of code. It just does a procedure call. And what this code does is say, OK, what keyboard should I read from? And once it knows, OK, I'm reading from this particular keyboard buffer, it's going to go off and read a character from that buffer. And so the reason it's a procedure is it has to worry about input-output pointers and dealing with the circularity of the buffer and things like that, all of which is below the level of abstraction we're interested in. We just want to say, give me the next character from the buffer. And I stick, the user is the C name for that M-state data structure. And we basically stick that value into the R0 slot. And so register 0 slot. So then when we return to the user, voila, we'll reload, this particular location will end up being loaded into the actual hardware R0. So when the user program starts to run, there's the character. So this is all great except for one little detail. What happens when there's no character to be read? Well, what would you like to have happen? Yeah. I'm sorry? Yeah, so the idea is that typically the so-called, most of the I.O. that you do, at least the simple I.O. is called synchronous I.O., which when you go off and ask for a character, you don't expect to start executing until a character is available. It's like saying, when there's another character available, give it to me and start me running again. Otherwise, just don't bother. So that's what a so-called synchronous call, a blocking I.O. call. Right, the idea is I'd only want to resume execution when there's an actual character. Most operating systems also support asynchronous I.O. calls where you can go check, and if there isn't one, it gives you back a special flag saying, I'm sorry, there isn't one, maybe you want to go do something else. So in this case, what should we do? So proposal 1, which turns out to be a very bad proposal, is to simply sit around and wait in the kernel, just sit there and wait until there is something to read. Okay, and that fails, and it fails for a reason we discussed last time. What happens when you start looping in the kernel? Well, nothing is a good description. Basically, once you start looping in the kernel, you never stop looping in the kernel. I mean, it's something you get to enjoy for the rest of your natural life, or until the user reaches over and presses the reset button. And so the idea is the machine basically goes dead because not all the interrupts are disabled when we're in the kernel. So this strategy of saying, okay, I can't just sit here and wait in the kernel waiting for another interrupt to happen where the character will come in from the keyboard. I actually, if I loop in the kernel, no interrupts will happen. So bad idea. So this is, we wrote this and immediately your friend leaned over and said, bzzz, doesn't work. Okay, so here is a different way to write that busy wait loop, okay? And you look at it and you go, this is a very strange loop. So first figure out what that code is doing. So if the keyboard buffer is empty, this is what it does. What does that do? It subtracts 4 from the current value of the XP register, the user's XP register. Wow, what does that accomplish? Well, what was stored in the XP register of the user? I'm sorry? Oh, the PC plus 4 of, in this case, the illegal operation, which was, so if I subtract 4 from the XP, I'm basically backing up the XP register, so it now contains the address of the supervisor call, in this case, the read key supervisor call. And what will happen when I resume execution? See, I don't return anything. I just say, okay, start running the user. What instruction will the user mode program execute when it resumes? Yeah. It'll do the supervisor call again. Okay. And you say, boy, that's a pretty complicated loop. Why did we gain by all this thing about basically telling the user mode program to re-execute the supervisor call? What was gained by doing that? We exited the kernel, we got back to user mode, and what can happen in user mode that can't happen in the kernel? Interrupts, the very thing we're waiting for. We're waiting for the interrupt from the keyboard saying, please do that. Okay, so does everyone sort of get the idea? The idea is we're writing a loop that returns to user mode. We haven't finished the execution of the supervisor call, so what we're doing is we're just re-executing it again and again and again. Okay. Eventually, during that one instruction worth of user mode, if somebody types a character, that interrupt will be serviced instead of executing the supervisor call. And then finally, we have a character return. Does everybody understand what we've accomplished? Now you can say, that's awfully inefficient. Why do we keep trying something that we have a pretty good idea will fail? So let's fix that. And there's a couple layers of fix. The first layer of fix, okay, so this works, it just wastes a lot of time. You're sitting there saying, I'm trying to play World of Warcraft over here, and this stupid email program it uses this entire time slice checking to see if I've typed the next character of my email message. Okay, and so I'm sort of wasting a lot of time on an event that hasn't happened yet, waiting for an event that hasn't happened yet. Okay, so step one in our fix is to not only back up the program counter to re-execute the supervisor call, we call scheduler. What does that accomplish? What do we get by calling that? What does a call to scheduler do? It goes to the next process. So this is effectively saying, okay, next time you start running me, okay, that's this line up here is saying, next time you start running me, please re-execute the supervisor call. This line of code is saying, but don't run me right away. Go run everybody else. So the scheduler will, in a round-robin fashion, deal with all the other processes, and then it will come back when it's this process's turn again, and it will check to see if a character's come in the meantime. Right, so what we're doing is when we do something, we're waiting for some event, typically we yield, it's called yielding. You yield the rest of your quanta, and you simply go off and let everybody else run, and then you come back. Everybody sort of get the idea? So this is just a way to improve the efficiency of this time sharing system. Okay, so basically we get to do more real work and less busy work of just sitting around in a loop waiting for an event that hasn't happened yet. Okay, and this really gets at the heart of why time-sharing systems tend to work. Obviously, if you have a bunch of user mode programs which are, CPU bound, in other words, they're just running lots and lots and lots of numeric code, time-sharing doesn't actually buy you much because you're just giving everybody a little shot to run. But if everybody says, I could run all day, what you've done is to take a job that would take 1 hour if you had the entire machine, and now it takes 10 hours if you're sharing the machine amongst 10 separate processes. And you say, well, what have I gained by doing that? And maybe it actually takes 10 hours and 30 minutes because you're spending a little bit of time simply in the overhead of going from process to process in the scheduler overhead. However, mostly processes are waiting for something. And so this notion of when you go into a state where you're really waiting for something, you give up your shot at it is really what makes time sharing make a lot of sense. It's a convenient program abstraction to say, look, I have an entire machine to myself. I don't have to worry about whoever's running. So it makes it easy to write user programs, okay? But it doesn't cost much to every once in a while run me, say I'm not ready yet, and then you go run everybody else. Okay, everybody sort of got the program? Well, there's one more fix we can do, which sort of solves even the don't bother to run me until the right thing has happened problem. This is a slide full of lots of words, but so here I was. This was in the middle 70s, and we had just gotten Unix version 2. Okay, so you know that's way back. Dinosaurs walk the earth sort of times, and you know I loved reading you know Ken Thompson's code, so I was looking through and I said, what is this? Look at what he does. This is a very clever thing he's managed to do, and of course this has been built into kernels. You know, this is the first time I had seen it, the first time I'd actually been able to look at operating system code. Okay, and the notion is we're going to, instead of calling scheduler, we're going to use. There's going to be two routines. The supervisor calls will use a routine called sleep, and they pass in a reason. Okay, and the interrupt routines will use a thing called wake up, which will wake up everybody who's sleeping on that reason. Okay, so you're going to go home tonight. You're going to say, I am dead tired. I'm going to take a nap. Okay, so rather than waking up every minute and say, is it time for dinner? Is it time for dinner? Is it time for dinner? You probably will tell your roommate, you know, pin a little note on your blankie and say, wake me when it's time for dinner. Okay, and your roommate, who for some reason isn't falling asleep, I don't know what happens if you all fall asleep. Does that ever happen? You go down to the dining hall and it's empty and everyone's zoned out? Okay, never mind. Okay, so what happens is that, you know, the scheduler comes in and says, wait, there's no reason to even start this process. It's sleeping, waiting for something to happen. When the something has happened, I'll wake it up and start running it again. And so the technical details are, I'm going to go to sleep and I'm going to give a reason. It's just an arbitrary binary number. Typically, it's the address of some buffer that you're waiting for something to appear in. Okay, and since that's a unique kernel location, it has, so that is an easy way to generate a unique number, a unique reason to go to sleep. What that does is it fills a special entry in your process control block called the status entry with that reason. So that's the little note pinned on the blankie. Right? The idea is that I'm going to go to sleep. Here's when you should wake me up. Okay. And the scheduler basically only runs processes that are active, in other words, that have a zero status. If you have a non-zero status, you're asleep and you're waiting for something. So the scheduler simply skips over you when it's considering the round robin. It simply just skips over you. It doesn't even bother considering you until your status is back to zero again. Now when I get a wake-up call from the keyboard down here, it's going to say, I've just stuck something, you know, put something in this buffer. Why don't you wake up anybody who's waiting on that buffer? And so what wake up does is it goes through the process table looking for everybody who's sleeping, waiting for something from that buffer. Typically it's only one thing, but conceptually it could be many different processes. You could be sleeping, waiting for some event. Okay, it sets their status to zero, meaning that they're ready to be run again. Now they may put themselves back to sleep if they discover that it's not quite ready yet, but at least something has happened that would cause this process to want to run again. And so by setting the status to zero, now the next time the round robin scheduler gets to you, away you go. So next time you fall asleep in 6004 lecture, remember to pin a note. When should we wake you up? Should I wake you up when the professor looks at you? No. I actually had a student once who raised his hand and said, I have a question. I said, oh, I was in the middle of some slide. I'll get to you at the end of the question. He managed to fall asleep before you know, it wasn't that long. I mean, it wasn't like I spoke for 30 minutes. You know, a minute later I turned to him and he's, so I thought that was particularly relaxed. You know, you have to be really cool about school to be able to fall asleep after asking a question. Now, as it turned out, he did his master's thesis with me, so it was actually a great way to be introduced. He came down afterwards and we got to talking. You don't have to go to that route. You could just come down and start talking, really. It's okay. Okay. So anyway, the sleep-wake-up mechanism is a very elegant solution to when only run processes when they're needed. Is there any basic questions? So that's sort of the story about how these supervisor calls actually interact with I/O devices. It's sort of this two-pronged approach. Devices fill up buffers, supervisor call empty buffers, and the kernel deals with what happens when there's nothing in the buffer to pass along. You know, what should we do? Okay. So for the rest of this lecture, I'm going to sort of shift gears a little bit and talk about real time. Okay. So up to now, everything's been virtual time. Everybody gets a little bit of time to run. We share it out equally. No one is busy looking at their watch. Okay. Everybody's saying, fine, I'll get to run for a little bit. Somebody else gets to run for a little bit. Okay. But there are applications for computers where what we want to do is to use computers to deal with situations that have real deadlines. In other words, we're not particularly interested in saying, oh, whenever you get to it is good enough. We really want to say, look, you have to, wake up and do something about this. Maybe a classic example is, how airbags work. The accelerometer goes, thwing, you've just run into the bridge abutment, okay, and now you need to release the airbag. You can't wait till the kid in the back seat finishes this round of wow, right? I mean, you have to sort of say, no, this would be a good time to really run this program. Make sure we, turn on, actuate the airbag, within 5 milliseconds. I was actually surprised when you look at the timing for airbags. It actually takes a long time for a crash to happen compared to computer instructions. Right? You can execute millions and millions of instructions as your car is slowly. So keep that in mind. God, I still have a million instructions I can do before. Yeah, okay. Okay, so the question is, how do we adapt what we're doing to take in the notion of real time? Alrighty, and the problem is that we've sort of abstracted time out of everything that we've been doing. Okay, time typically tends not to be something that computer programs really care about. How do we make, what's our way of making, making computers work in real-time situations? And the thing is, we've just discovered, often an event triggers a small action, but then we want some user mode program to actually run and do something. And what I really want to do is to sort of explore, how do we figure out what the computer should actually be doing moment to moment, and not just simply being fair and going through things in a round-robin fashion. Maybe there's a notion of some things have higher priority than other things. So we're going to talk about that. Okay, so we have hard deadlines. What we're going to do is to come up with a so-called, look at what it would be built into most real-time operating systems. A lot of the controllers that the world runs on are basically run on one or another of the real-time operating systems. They're sort of, they have Linux-like services often, but they're really sensitive to, you can say, I want this program to run within, 200 microseconds of this happening, and the real-time operating system will actually be able to meet those sorts of guarantees. Okay. So what I'm going to do is sort of give you an abstract view of the world. So there's some sort of request, bridge abutment, accelerometer, ding, okay, deploy airbag request, and then we have this notion that some amount of code has to run, okay, and there's some amount of time that elapses between when the request is made and when the code that needs to run to service that request happens. It takes service time, some number of microseconds to run that code, and the goal is to meet some deadline. We want to make sure that the service routine completely finishes execution before some deadline. So that's sort of the abstract setup of the problem. And what we have is many such things that are all going to be wanting to sort of collaborate together and use a single piece of hardware. And our discussion is what scheduling algorithm should we use to guarantee that we can meet the real-time constraints specified by the deadline with respect to the request, given that we know the service time. Okay, what happens if you miss deadlines? Typically not such good things. Okay, okay, so you miss a character, you'll see the typo in your document, no big deal. It might be that you drop disk blocks and your disk gets corrupted, or it might be that 3 Mile Island goes and you get this beautiful picture in the evening news, and we all go, dang, I wish somebody had written the code a little better. Okay, so the idea is that the so-called hard real-time constraints are a very interesting and actually important class of things. Given that computers sort of run the world these days, it's important that they be able to deal with these hard real-time constraints. Where does the latency come from? Why don't I just start something right away? Well, it obviously takes a little bit of time to save away registers and set up the kernel stack and change the MMU to start getting ready to run a new user program. So there's all this sort of stuff that we need to deal with. Okay, so when we write our operating system, we can work hard to make that as efficient as possible. Some instruction set architectures have instructions that take a long time to run, many, many, many cycles. It used to be fashionable to build in instructions that evaluated polynomials of arbitrary degree. You know, some big expression involving x to the 17th power plus x, you know, coefficients and all that. And they say, look, one instruction, eval polynomial. You know, you put x in a register and poof, it comes back. But it would take zillions of cycles to actually do all the arithmetic. Okay, or, you know, move this 4 gigabytes of memory from here to here in physical memory. So those are all conceptually useful, but they represent instructions that potentially increase the latency before you get a chance to take an interrupt, you know, at the end of the current instruction and deal with it. Okay. And then finally, of course, if we are explicitly disabling interrupts because we're in the kernel, or because we've asked the kernel to disable interrupts so we can perform some sort of atomic operation on a shared data structure. So these are all examples of things that might improve, you know, impact the latency. Real-time operating systems sweat these details constantly, and they put a lot of restrictions on what you're allowed to do in order to avoid all these sources of high latency. Okay. All right, so here's a little toy system. We have 3 devices. We have a keyboard. It takes 800 microseconds to, or whatever the nanoseconds, microseconds say, you know, of code that has to run to serve as keyboard interrupt. We have a disk and we have a printer. And so how long is it before any particular device gets to run? Well, in the simplest of things, everybody just stands in line and waits their turn. So if, in fact, we get a disk interrupt, a printer interrupt, and a keyboard interrupt, all sort of one after another, then the poor keyboard might have to wait for both the disk and the printer to finish. So it's going to be a total time of 500 plus 400, 900 microseconds before it gets a chance to start running. Okay. So that would clearly impact the deadline by which the final instruction of the keyboard handler gets to run. I can do similar arithmetic for both the disk and the printer, and what we can see is that, in fact, the latencies are quite large before we start executing, you know, in this case, the disk code. And you look at this and you go, wow, I mean, keyboards happen at user speeds, right? I mean, even for the world's best typist, it's going to be, you know, tens of milliseconds between characters. Okay, whereas disks and printers are a little faster. I mean, they're still a mechanical device typically, so or involve a network transfer. Disks tend to be much higher performance. If you really want to get maximum throughput from your disk, you can't wait very long before sending it the next request after it finishes the current one. Otherwise, your disk will appear to be much slower. Okay, so this notion of everybody just waits their turn and you wait behind everybody else, that can lead to very long latencies, particularly when there's a lot of people looking for a lot of different devices looking to be serviced. So we're going to talk about 2 different types of priority now. Now we're going to say some devices get to run before other devices. There's going to be weak priority and strong priority. And there's a very simple distinction. In a weak priority system, I always finish what I'm doing in the kernel. So if I've started the printer routine, it's going to finish before I decide to do anything. Once I'm ready to consider what task to run next, okay, I will look to see which task has the highest priority. So a weak priority scheme doesn't involve any what we call preemption. There's no stopping what you're doing. But there is the notion of using a priority to decide what to do next when you're about ready to start something next. Everybody sort of get that? So that's what means. So weak means no preemption. Strong, just looking ahead a slide, strong will mean interrupt me if something of higher priority comes along. Okay, so if we actually look at, if we establish a weak priority, in other words, the disk has a higher priority than the printer, which has a higher priority than the keyboard, okay, typically reflecting the sort of speed at which you hope interactions will be happening with the devices. Now I can go off and look at the actual latencies, the worst case latencies. Now the keyboard, because it has the lowest priority, typically will have to wait for both the printer and the disk to finish. So its latency is no different. Okay. The disk, on the other hand, at the worst case, will have to wait for the keyboard to finish, okay, but then it will always be next in line because it has a higher priority than the printer. Okay, and finally, the printer might have to wait for the keyboard to finish, because it had started and we're not going to interrupt it. And then it has to wait for the higher priority device to finish, in this case, the disk. And so it might have to wait a total of 800 plus 500 or 1300. And the thing to notice here is the disk actually will get service slightly faster because it's at the front of the line. Okay, so here you are at the airport. You're waiting in this long TSA line. And you're sort of going, I got a flight, you know. And so one way in which the TSA could run the TSA line is the little old lady who's looking through her purse and, oh yeah, here's a picture of my grandchild. I'll show the ID already, you know, and we want to go. And so, you know, if you're not going to interrupt her, everybody else is, you know, so that, it helps a little bit to say, okay, after grandmama's finished, who should I do next? You know, who's going to miss their flight? Okay, that's a little bit of a help. But clearly there's something we want to do. Right? If you were there, what you really like to do is say, excuse me, Grandma, could you just wait one moment? I want to take care of Mr. Type A over here, who obviously is going to split a gut if he doesn't get through to his gate in a big hurry. So there's a notion now of interrupting what you're currently doing to do something else. Okay, so the need for preemption can be pretty obvious. You know, there'll be lots of times when I'm standing in a long TSA line and I say, I'm admiring all the first class passengers who are all going like this, you know, and I'm going, when am I going to get to do that? So the notion of a priority is actually pretty helpful, and not so much for first class, but in terms of making sure that we put our attention on the things that need to be, that have a critical time deadline. Okay, and occasionally that happens, right? Occasionally somebody wanders through, say, on the line saying, anybody on the Dallas flight that's leaving in 2 minutes? And then they sort of push you through. Yes?
I have a question, like on the last slide. If there were like many calls, like keyboard was going and then this got called a bunch of times, is there any way to like eventually slip one printer in, or like what if this just keeps getting called and then nothing?
We'll look at recurring interrupts in just a second. I mean, that's obviously an issue and one that real-time operating systems have to pay attention to. So it's a great observation. Okay, so if I allow devices to be preempted and I give them priorities, so in this case, the highest priority is the numerically highest priority, priority 3 is the highest priority. That means that essentially the highest priority device always gets to interrupt execution of any lower priority task that's going on. So the disk basically has almost no latency. It does just the cost of the context switch. And it always gets to stop what's happening. The printer, okay, has a latency. It might have to wait for a disk interrupt to have a higher priority, but then it gets the next bite at the apple. And the poor printer now is, you know, sort of behind everybody. Okay, but what we've really done now is we've improved the latencies now for these high priority devices. And that was our goal. Okay, so how do we implement priorities? Well, what we're going to do is instead of just having a user mode, kernel mode bit, we'll have, you know, we'll maybe assign priority 0 to mean user mode programs, and they just get run in some round robin fashion. So users are at the low end of the totem pole in this very simple priority scheme, and they all have equal priority. Not that you couldn't improve on that too. But then we're going to use a couple more bits in this case, the high order bits of the program counter. Typically, they're in a separate register to keep track of what priority we're running at. And whenever an interrupt comes along, we look at its priority and we say, is it higher than the current running priority? If so, make the interrupt happen. Okay. If not, it's like, you know, like you were in kernel mode before, no interrupt will happen. So the kernel has different levels of priority, and only a higher level of priority can interrupt the current priority. Okay, recurring interrupts, as we were just commenting, you can make it so that interrupts happen at a certain frequency. There's clearly a maximum frequency at which interrupts can happen and still have enough time for everything to go on, right? So the service time for every interrupt obviously takes a certain percentage of the CPU, and altogether we have to make sure we're less than 100% of the CPU. Here you can see the poor keyboard is forever being aced out by printer and disk interrupts, which are happening at much higher frequency. The only net effect of this is, of course, the keyboard finishes much later, you know, because it keeps getting interrupted. And figuring out what whether their keyboard will meet its deadline involves figuring out how much of the CPU is being used by all the higher priority service routines. Okay, but there's no magic. It's just a piece of arithmetic the real-time operating system does and says, I can't meet that schedule, I am sorry. Okay, with the constraints that you've given me, I cannot guarantee the keyboard will finish in time. So now you have to reorganize the priorities or change the frequency of the recurring interrupts, so forth and so on. This notion of, is there enough time to do everything? Well, what I can do is I can look at how much time it takes to actually service the interrupt, how many times a second that interrupt happens, and calculate the percentage of the CPU devoted to servicing that device. And so here I am. I've done all that arithmetic for you in this slide, assuming that the disk takes 500 microseconds and happens 500 times a second, so forth and so on. So after you do all this arithmetic, obviously if the number is less than 0, this is a bad news. The user mode program gets the rest. Okay, so I'm going to start an example which I won't get to finish, but you'll be able to look at it in recitation when we cover the interrupts in real time. Alrighty, so we're going to visit the space station. This was inspired back when one of the Russian supply ships actually bumped into the space station, and you're sort of going, what happened there, right? And so we like to imagine there was a problem with their interrupt system, that they simply weren't giving enough service. They weren't meeting the real-time constraints of the guidance system. What I suspect is that somebody was actually playing a game on their phone or something, and oh my God, look at that. Sorry. Okay, so there's 3 tasks: supply ship guidance, gyroscope, and cabin pressure, all of which are important things, particularly cabin pressure. There's interrupts that happen at a certain, interrupts happen at a certain interval. This is the amount of time it takes to service those interrupts, and here are the deadlines. Okay, in other words, within 20 milliseconds of a gyroscope interrupt, in other words, the space station is starting to veer, you should do something about that. What we need to do is we need to be able to run a 10 millisecond service routine, okay, so that it's completed execution 20 milliseconds after a gyroscope interrupt has happened. Okay, so what we've done here is tried to specify all the different pieces. Can we make this work with a weak priority system? Well, let's see. Okay, so the maximum service time. Let's think about what this question is asking. We got a question mark. How long can I spend servicing? Okay, in this case, the cabin pressure. So we're asking now remember what happens with a weak priority system. Once I start running a task, it's going to run to completion. Okay, and what I'm going to do is I'm going to look at the allowable latency. I'm going to say I have to meet this 25 millisecond deadline, and I have to spend 5 milliseconds to do that. That means the longest I can wait before starting this task is 20 milliseconds, 25 minus 5. The longest I can wait before starting the gyroscope task is 10 milliseconds. The deadline at 20 minus the 10 it's going to take to actually do the service routine. So that means that I can't start anything that runs for more than 10 milliseconds, otherwise I risk blowing the gyroscope deadline. In other words, a gyroscope interrupt could happen, and in a weak priority system, if I'm just started something that takes longer than 10 milliseconds, this routine will not start, run for 10, and finish in time to meet its deadline. So we have a hard upper limit to how much time I can spend servicing cabin pressure, lest I risk blowing the gyroscope deadline. So now you can see this starts to get it's an interesting puzzle, trying to figure out how all these things can fit together. And what we discover is that without that constraint, this system won't work. Okay, is there a weak priority that meets the constraints? It turns out there is. We can use the so-called earliest deadline algorithm. So if there's a schedule that will work with weak priority, the earliest deadline scheduler will work. In other words, you pick the thing that you do next. This is very familiar to you. When you go home and decide it's actually time to start work, which is a separate question, and you say to yourself, what is it you start working on? Well, you look at everything that's due, and you say, what's due next? Maybe I should do that. And so this notion of earliest deadline scheduling is actually it's pretty easy to prove that if any schedule can meet the deadline, the earliest deadline schedule can meet the deadline. So this is earliest deadline. So you can see the gyroscope has the earliest deadline, then supply ship, and then cabin pressure. Okay, what fraction of the time? I just, I have to run for 5 milliseconds every 30 milliseconds, and I have to run for 10 every 40 and 10 every 100. I can compute the total amount of CPU time it takes to do that, and discover that I've used up, 52% of the processor just servicing interrupts, so I have 48% of the time left to actually run. Okay, and the worst case time I can figure out using the weak priority scheme and just remembering that higher priority, a task has to finish and then anybody else who's higher priority than me has to run. I can figure out the sort of worst case deadline, time until completion. You can do all of that same arithmetic using a strong priority system, and we'll go over that in section. So I'll stop there. Imagine things bumping into space stations or cars hitting bridge abutments and realize that if you're going to use a computer, you need to think about real time.